Hello, my voice is audible.
Audible.
Hello. Okay, now.
Sir, audible,
Like,
sir.
it is a trees. Okay, screen is visible. Trees.
Yes, sir.
Okay, now. Thank you. Here today we will discuss that is a trees. Trees are it is a aim and objectives. It is a trees and the forest and the centers in the trees and the spanning trees. That is the first topic what we will discuss here, and bring the relationship between the number of vertices and the edges. Last class మనం graphs గురించి డిస్కస్ చేస్తాం. In the graphs is the vertices and the edges గురించి connected trees గురించి డిస్కస్ చేస్తాం. ఆ graphs it is a connected graphs to be the trees. How it will be the graph will be the trees అనే దాని గురించి మనం డిస్కస్ చేయాలి. ఇందులో షార్టెస్ట్ పాత్ పాయింట్ ఆఫ్ ఇట్ ఇస్ వెయిటెడ్ అండ్ కనెక్టెడ్ గ్రాఫ్స్ గురించి డిస్కస్ చేస్తాం. ఇందులో వన్ లాంగ్ క్వశ్చన్ ఇస్ లాస్ట్ ఫోర్త్ పాయింట్ మీద ఉంటుంది. వన్ క్వశ్చన్ లాంగ్ క్వశ్చన్ కంపల్సరీ ఉంటుంది. It is a very important role into the daily life. It is a family of the is connected with the member of the family members. That number of family members means it is a one tree. It is a one tree means it is a branch will be there. That is a one tree. It will be the plant and all how it will be they come into the branches. So that all will be the representation of the trees. అంటే ఒక ట్రీ తీసుకున్నట్లయితే అందులో ఉన్నటువంటి ట్రీకి ఎన్ని కొమ్మలు ఉంటాయి, అన్ని ఆకులు అవన్నీ దట్ ఈస్ ఆల్ విల్ బి కమింగ్ వన్ ఆఫ్ ద ట్రీస్. ఇవన్నీ కూడా ఏంటంటే వర్టిక్స్ వన్ వర్టిక్స్ రిప్రజెంటేషన్ మెంబర్స్ ఫ్యామిలీ అనుకుంటే అందులో కూడా ఎడ్జెస్ ఆర్ రిప్రజెంటేటివ్ ద పేరెంట్స్. ఎడ్జెస్ ఎక్కడైతే రిప్రజెంట్ చేస్తుందో అది పేరెంట్స్ అంటాము. వర్టిక్సెస్ వచ్చేసరికల్లా అందులో ఉన్నటువంటి ఫ్యామిలీ మెంబర్స్ అంటాం. ఆ పేరెంట్స్ ఎలా ఉంటుంది, ఫాదర్ అండ్ మదర్ ఉంటుంది, చిల్డ్రన్ అండ్ రిలేషన్షిప్స్ అన్ని కూడా అందులో ఉంటుంది. వర్టిక్సెస్ రిలేషన్స్ రిప్రజెంట్ ద మెంబర్స్ ఆఫ్ ద ఫ్యామిలీ. ఎంతమంది ఉంటారు, 4 or 5 or 6 అనేటువంటి కూడా వర్టిక్సెస్ చేస్తుంది. Trees are very useful in the computer science, in the particularly it is at a different, not only the one particular mathematics we will use into the various areas. It is a network system, kotta design systems develop avutunnayi. Okay, artificial intelligence lo, network theory lo, network analysis, internet of things, iటువంటి kotta concepts lo ee weighted trees అనేటువంటిది యూజ్ అవుతూ ఉంటుంది. Next, it is coming to the forest and the trees. It is a graph is said to be the acyclic if and only if it is contains the no cyclic. నో సైకిల్స్ లేవు అనుకుంటే ఆ సైకిల్ అని పిలుస్తాం. ఇన్ గ్రాఫ్ లో సైకిల్ కావాలి. సైకిల్ అంటే ఏంటిది, ఫస్ట్ మీరు ఒక ఊర్లో ఉన్నారు, ఒక టూర్ అనేటువంటి ప్లాన్ చేశారు. టూర్ అంటే వేరియస్ ప్లేసెస్ లో విజిట్ చేసేసి అన్ని ప్లేసెస్ విజిట్ చేసేసి ఎక్కడికి రావాలి, మళ్ళీ నీవు సేమ్ సిటీకి రావాలి. నీ ఓల్డ్ సిటీ సేమ్ సిటీకి వస్తే దట్ ఈస్ కాల్డ్ యాజ్ ఏ సైక్లిక్ అని అంటాం. అంటే ఫస్ట్ నువ్వు ఏ సిటీ నుండి మొదలు పెట్టావో ఆ సిటీ నుండి అదర్ సిటీస్ అన్ని కూడా విజిట్ చేస్తూ సేమ్ సిటీకి వస్తే అంటే రిపీటెడ్ కాకుండా దట్ ఈస్ కాల్డ్ యాజ్ ఎ సైకిల్. ఆ సైకిల్ అనేటువంటిది మధ్యలో బ్రేక్ అవ్వకుండా ఉండాలి. ఒకవేళ మధ్యలో బ్రేక్ అయితే దట్ ఈస్ కాల్డ్ యాజ్ అసైక్లిక్ అంటాం. అదే దాని మధ్యలో బ్రేక్ అయితే మాత్రం దట్ ఈస్ నో సైకిల్ అని పిలుస్తాం. సో ఒక గ్రాఫ్ అనేటువంటిది ఈస్ టు బేస్ అసైక్లిక్ ఇఫ్ ఇట్ ఈస్ ఇట్స్ కంటైన్ నో సైకిల్స్. నో సైకిల్స్ కానీ లేకపోతే ఇట్ ఈస్ కాల్డ్ యాజ్ అసైక్లిక్ అని చెప్తాం. అంటే ఇదంతా గ్రాఫ్ లో మనం డిస్కస్ చేస్తే వన్ స్మాల్ కాన్సెప్ట్. నెక్స్ట్ ఇట్ ఈస్ కమింగ్ టు ద అసైక్లిక్ గ్రాఫ్ ఈస్ కాల్డ్ యాజ్ ఎ ఫారెస్ట్. ఎప్పుడైతే సైకిల్ అయింది అనుకోండి గ్రాఫ్ అంటాం. ఆ గ్రాఫ్ లో వన్ పార్ట్ ఈస్ సైకిల్. సైకిల్ అండ్ ఫారెస్ట్ అనేటువంటిది టూ టూ బ్రాంచెస్ అంటే టూ కనెక్టెడ్ సెట్స్ కింద ఉంటాయి. ఒకటి ఫారెస్ట్ సైకిల్ అయితేనేమో సైకిల్ అంటాం. అసైక్లిక్ అయింది అనుకోండి ఇట్ ఈస్ కాల్డ్ యాజ్ ఫారెస్ట్. అసైక్లిక్ ఈస్ కాల్డ్ యాజ్ ఎ ఫారెస్ట్. ఏది ఇవన్నీ గ్రాఫ్ లోపల థింగ్స్ ఐఎమ్ డిస్కసింగ్. గ్రాఫ్స్ అంటే లాస్ట్ క్లాస్ లో బోర్డు మీద చూపించాను కనెక్టెడ్ సెట్స్ ఎలా ఉంటుంది. అంటే వన్ వర్టిక్స్ టు వన్ ఎడ్జెస్ కనెక్ట్ అవుతాయి. టూ వర్టిక్స్ మధ్యలో వన్ ఎడ్జ్ వస్తుంది. అట్లా అన్ని ఎడ్జెస్ అన్ని కనెక్ట్ అవుతాయి. దట్ ఈస్ కాల్డ్ యాజ్ గ్రాఫ్ అన్నమాట. అది సైకిల్ అంటే క్లోజ్డ్ అయితే ఇట్ ఇస్ సైక్లిక్, నాన్ క్లోజ్డ్ మీన్స్ అసైక్లిక్ అని పిలుస్తాం. నెక్స్ట్ కనెక్టెడ్ అండ్ అసైక్లిక్ గ్రాఫ్ ఈస్ కాల్డ్ యాజ్ ఎ ట్రీస్. దట్ ఈస్ కనెక్టెడ్ ఫారెస్ట్ ఈస్ ద ట్రీస్. అంటే అసైక్లిక్ గ్రాఫ్ ఈస్ కాల్డ్ యాజ్ మనం ట్రీస్ అని పిలుస్తాం. కనెక్టెడ్ అది కనెక్ట్ అయి ఉండాలి. కనెక్టెడ్ ఎంతవరకు అయి ఉండాలి? హాఫ్ ఆఫ్ ద 50% కనెక్ట్ అయితే చాలు. ఇట్ ఈస్ కాల్డ్ యాజ్ అసైక్లిక్ అని పిలుస్తాం. నెక్స్ట్ ఇట్ ఈస్ ఇందులో ఒకటి ఉన్నటువంటి ట్రీస్ లోపల ఒకసారి చూడండి ఐసోమార్ఫిక్ గ్రాఫ్స్ ఆన్ 4 vertices. 4 vertices తీసుకున్నాను అనుకోండి. నాన్ ఐసోమార్ఫిక్ గ్రాఫ్స్ ఉంటాయి. అంటే ఒకే షేప్ లో ఒకే రూపంలో ఉంటే అది ఐసోమార్ఫిజం. అదర్వైజ్ ఇట్ ఈస్ నాన్ ఐసోమార్ఫిజం. ఒకసారి చూడండి ఇందులో నాన్ ఐసోమార్ఫిక్ గ్రాఫ్స్ ఆఫ్ ద 4 vertices వచ్చేసరికల్లా ఎన్ని vertices ఉన్నాయి, ఎన్ని డాట్స్ ఉన్నాయి, ద డాట్స్ ఆర్ కాల్డ్ ఎస్ vertices అని అంటారు. డాట్స్ ఆర్ కాల్డ్ ఎస్ vertices అని అంటారు. నెక్స్ట్ ఇందులో ఉన్నటువంటి దాంట్లో ఒక చూడండి ఒక వర్టిక్స్ నుండి అనదర్ వర్టిక్స్ మధ్యలో కనెక్షన్ ఈస్ కాల్డ్ ఎస్ ఎడ్జెస్. ఎన్ని ఎడ్జెస్ ఉన్నాయి? 3 ఎడ్జెస్ బట్ 4 పాయింట్స్. 4 పాయింట్స్. దిస్ ఈస్ కాల్డ్ యాజ్ నాన్ ఐసోమార్ఫిక్ గ్రాఫ్స్ ఆన్ ద 4 vertices. వాడు ఎగ్జామ్ లో అడుగుతాడు ఎక్స్ప్లెయిన్ అబౌట్ నాన్ ఐసోమార్ఫిక్ గ్రాఫ్స్ ఆన్ 4 vertices అంటారు. అప్పుడు మీరు సింపుల్ గా డ్రా చేసేసి 2 marks 5 marks క్వశ్చన్స్ డైరెక్ట్లీ యూ డ్రా దిస్ వర్క్ గ్రాఫ్. 4 vertices and 3 edges connect చేసేసి దీస్ ఆర్ కాల్డ్ యాజ్ ఏ నాన్ ఐసోమార్ఫిక్ గ్రాఫ్స్ ఆన్ ద 4 vertices అని చెప్పగలిగితే చాలు. నెక్స్ట్ ఇట్ ఈస్ నాన్ ఐసోమార్ఫిక్ గ్రాఫ్స్ ఆన్ 5 vertices. 5 vertices తీసేసుకొని అందులో కనెక్ట్ చేసేస్తే సరిపోతుంది. నెక్స్ట్ ఇందులో ఉన్నటువంటి దాంట్లో అబ్జర్వేషన్స్ నేను అబ్జర్వ్ చేస్తాయి. ఇట్ ఈస్ కే ఆఫ్ బి. కే ఆఫ్ బి మీన్స్ ఇట్ ఈస్ బి గ్రేటర్ దెన్ ఆర్ ఈక్వల్ టు 3, 3, 4, 5, 6 సో ఆన్ లైక్ దట్. అప్ టు ఎన్ వరకు తీసుకుంటే అప్ టు ఎన్ Hello, my screen is visible.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, thank you. Thank you, Anita. Now here, discussion is comes to the episode. Now here, non-isomorphic graphs on the five vertices. Draw all the cycles, vertices గురించి discuss చేస్తాం. In a tree, one second. చెప్పు ఏం మాట్లాడు ఎవరు మాట్లాడాలి ఏం మాట్లాడాలి మీరు త్వరగా రండి రిగార్డింగ్ లేదా దేని గురించి ఎవడు రమ్మని లోపల రండి లోపల రండి ఫస్ట్ లోపల రండి ఎవడెవడు ఏం మాట్లాడుతున్నారు త్వరగా రండి నాకు టైం లేదు త్వరగా Hello? Sorry, actually, small. The result is obvious when the T is a trivial tree. If in a tree, any two vertices are connected by the unique path. This is an important theorem. In this theorem, the result in a obvious when the T is a trivial tree. Trivial అంటే ఏంది యూనిక్ ట్రీ. ఒకటే ట్రీ ఉంటే దాన్ని యూనిక్ ట్రీ అంటారు. అయితే ఆ యూనిక్ ట్రీ అయినప్పుడు అంటే యూనిక్ ట్రీ ఉందంటే ఏంటి యూనిక్ పాత్ కూడా ఉండాలి. సో అటువంటి టూ వర్టిసెస్ మధ్యలో కనెక్ట్ చేసినప్పుడు ఒకటే ఎడ్జ్ ఉంటుంది అని చెప్పడమే మనకి ఇక్కడ మెయిన్ ఇంపార్టెంట్ టాస్క్. ట్రీ అంటే ఏంటిది ఇందులో ఇట్ ఈస్ ఆల్సో కనెక్టెడ్ పాత్. ఆ కనెక్టెడ్ పాత్ గ్రాఫికల్లీ కనెక్టెడ్ పాత్ అంటే ఇది ఏది ఐసోమార్ఫిజం గా వచ్చి ఇందులో ఒకటి ఏదైనా టూ కనెక్టెడ్ గ్రాఫ్స్ మధ్యలో అసైక్లిక్ గ్రాఫ్ if and if it is connected continuous to the no cycles even now it is a characteristics of the trees it is a if in a tree any two vertices are connected by the unique path it is a proof point of I will take the T is one of the trivial tree I am taking here obviously u comma v are the any two vertices vertices kuda అందులో tree లో ఒకట అంటే గ్రాఫ్ లో ఒకట తీసుకుంటాం. Now suppose T is connected అంటే ఆటోమేటిక్ కనెక్ట్ అవుతుంది. ఎప్పుడు కనెక్ట్ అవుతుంది ఇట్ ఈస్ u comma v are any two vertices అయినప్పుడు ఆ రెండింటి మధ్యలో ఎడ్జ్ కనెక్ట్ అయితే ఇట్ ఈస్ కనెక్టెడ్. there is a path అంటే అక్కడ కనెక్ట్ ఎప్పుడైతే ఎడ్జ్ ఇస్ కనెక్టెడ్ then it will come into the path. Now it is coming to the path and say that it is a P1 path is called as a P1 from the U to V. Suppose there is another path would appear say the P2 from the U to V, another path U to V since P2 is not equal to P1. P2 is not equal to P1. There is an edge అనేటువంటిది అంటే P2 another two connected vertices and another two connected vertices. After that, suppose that there is a another path if we take P2 and P2 is not equal to P1. P2 is not equal to P1 means it's both are the different. So that it is a P1 there already it is a two P1 is a two vertices connection and P2 also two vertices connection. There in between we have a one edge is connected. Say that it is a E equal to and x comma y belongs to V of T. V means it is a graph లో vertices of the T అనేటువంటి tree కు edges ఉన్నాయని చెప్తుంది which is a P2 and not in a P1. If it is a P2 ఉన్నటువంటి any two vertices it is not into the P1. It is not into the P1 connection. P1 vertices is different and P2 vertices is different and P1 connection is different and P2 connection is different. At the time it is anyway it is both are it is not equal. So that it is a which is in P2 and not in a P1. So now P1 union in P1 union P2 minus C minus one edge is I am removing it. Both I am connecting and one edge is I am removing. So that x to y it is a walk in T it will be getting that. So it is there is a x to y is a path. So that P in the capital D. Now it is a P plus E is any cycle in T and there is a contradicts the acyclic nature of the T. Hence our supposition is a false. This conclusion is a proof of the theorem. So it is a anyway it is a two connections. So we have that it is a tree means what is it? Its edges are connected with the vertices. So it is a P1 union P2 also its edges are connected with the vertices. So that it is I am removing there is a one edge. What happens again? It will be having the connections one. So that it is clearly unique path is exist. Unique path is exist. Then we can say that connection is available in between the two vertices. Therefore, it is a tree that is called as a tree. This is overall information about that. So what is when it's in a tree, the two vertices are connected by the unique path. The two vertices are connected by the unique path. So that is P1 union P2 minus edge is clearly x to y. It is walk in T. Walk in T will be available. Next, it is coming to the 11.4.2. It's if G is a loopless graph. Loopless graph means it is a loop means it's a vertex itself. It is connected. Then it's called as a loop. Loop is not there. G is a loopless graph and any two vertices of the G I'm taking and it is connected by the unique path. Then G is a tree. Converse of the loop, which is the extra conditions of the loopless. If G is a trivial graph, then the result is obvious. Otherwise, by the hypothesis follows that the G is connected. Since G is a loopless and G is a no cycles of the length. Already cycle means it is a what is that? It is the one edge is started and connected to all the edges and it is coming to the starting point. That is called as a cycle. It is a starting point to ending point. When it will come, comes to the cycle.
Now he's asking the loopless. Loopless means it is one vertex itself. It is connection. That is called as a loop. If it is a loopless means that is the same connectivity is not there. At the time, two vertices of the G are connected. Two vertices are connected. Connected by the unique path. Unique path means it is a one edge. Then the G is called as a tree. G is called as a tree. So that it is anyway, it is an entire graph. Here I'm removing that is a one vertices. What happens? Anyhow, it is also tree. That is, I can say that it is a trivial graph. I'm taking the G is a trivial graph. Hypothesis of the G is connected, and since the G is a loopless, follows that is that G has no cycles of the length. One. And suppose G is a cycle, so G has a cycle C. The length is greater than or equal to 2. Let E be the any edge of the C. So with the edges, ends it's x comma y. Now it is the vertices of x comma y of the G are connected to distinct path. Namely, it is a C as a C to C minus E. The contradicts hypothesis. It is hence G has no cycles. No cycles. Therefore, it is a G is a cycle is not there means it's what is it? It is a tree only. So that it is a tree only. First, I have taken the graph, but it is a no connection in between that is any two vertices. At the time, directly we can say that it is called as a tree. That is a information I have given in the 11.4.2. It is important from the 11.4.3. Here, induction between the induction on the number of the vertices. Connectivities between the any two vertices. Let V of t equal to 1. Let V of t equal to 1 I am taking. Then it's a clearly t is a trivial. And epsilon of the t is equal to 0. And a trivial graph, if I take, that is a two edges, two vertices in between. If it is a connection is not there, edge is not there. At the time, V of t equal to how much? 0. So what happens? It's a one edge is there. That is I am thinking. What happened? It is clearly what I say. So it is 1 minus 1. 1 means it is the V of t. So V of t equal to V of t minus 1. We can write it for the mathematical induction from the t equal to n equal to 0. Next, V of t equal to, it is n is greater than or equal to 2 if I take resultant of the valid, result in the valid for the all trees, with the number of vertices is less than v. Now consider the t with the vertex v, so that t is a non-trivial. Let the edges, one edges I am taking with the edges of x comma y. X comma y are any two vertices from the V of G. It is a edge of the x to y path of the G in the T. So that is a falling, that is x minus y. In between one path will be the x to y. Therefore, T minus E I can take. T minus E in between connections I will remove. Hence, T minus E is clearly, if I remove from the one edge from the tree, what happens? It's a disconnected from the one edge only. So that it is the remaining edges if we take 1 equal to W of T, it is less than or equal to W of T minus E. That is less than or equal to W of T plus 1. So that 1 plus 1 equal to 2. It is 1 is less than or equal to 2. So what happens? It's a W of T minus E equal to 2. W of T minus E equal to almost 2. So it is a mathematical induction further. It is a explained at the greater than or equal to two case I am discussing. Now if I go for that, it is a unique I want to explain. No, it is a T1, T2, two trees I am taking. T1 and T2 be the components of the T. One T in that single T, I am taking the two T's. T1 one tree and another is another tree. That's the two graphs I am bifurcating. It is X belongs to V of T1, vertices of the one, and Y belongs to V of T2. Then Y belongs to V of T1. That implies X belongs to V of T2. Hence, mod V of T1 and mod V of T2 less than V of T. By induction hypothesis, we get that is a edges of T1 is equal to the mod vertices of the T2 minus 1. So edges of T2 equal to mod vertices of the T2 minus 1. Therefore, it is the since it is a one edge is clearly edge of the T equal to, it is edge of the T1 plus edge of the T2 plus 1. Therefore, it is clearly we can write that V of T1 plus V of T2 minus 2 plus 1. Therefore, it is called as a V of T minus 1. V of T minus 1. This is clearly, it is every vertex of the having exactly one of the T1 and the T2. So that it is a two, when we will bifurcate at that time also in between, also connection means one edge must be the needed. One edge must be the needed. So vertex of the V of T1, vertex of the V of T2 minus 2 plus 1. That is so that it is a V of T minus 1. Edges of vertex minus 1. So edge of T is equal to the vertices of the T minus 1. That is called as our required answer. Vertices of the T, it is called as our required answer. So edges of the T is equal to its vertices of the T minus 1 is our required answer. This is a, from the mathematical induction, I prove that is a n equal to 0 and n equal to 1. And after that, I'm going for that is a vertex of the n is greater than or equal to 2. I'm discussing that is a 2 points. It is clearly, it is a W of the t minus 2 e equal to 2. That is a vertex, it is a 2 when I consider. Then I will go for that is a compounds observation if I observe. At the time, I can discuss that is a total combination. Compounds means it is epsilon t1 plus epsilon t2 plus 1. So that it is edges of the tree is clearly, it's the vertex of the t minus 1. We got it. This is the overall idea about it. This is more important. Next, it is a coming to the non-trivial. If it's a trivial means it is only one tree if I consider. It's a non-trivial means it's a many trees if I consider. Non-trivial tree which is a v vertices of the v greater than 2. So that is a Euclid, already Euler's theorem we know that is a summation of the dimensions of the vertices. Dimensions of the vertices means one vertices after it is connections, how many we have, that is called as dimension. So dimensions are, it is clearly 2 times of the edges of the t, 2 times of the edges of t. So 2 times of the vertices minus 1. 2v minus 2. This is a already it is a from the Euler theorem we have written. Now what he is asking to prove that non-trivial tree has at least 2 pendant vertices. 3 pendant vertices are available. So the dimensions I am taking v greater than or equal to 1. So we have v belongs to what is the vertices on that I am taking one vertices. V1 is another vertices of the degree 1. So that it is all the vertices if I connections. If I take that in the t is greater than or equal to 2. So that it is a just now we got it 2v minus 2 is clearly greater than or equal from the first equation, dimensions based on that. It is greater than or equal to v1 of the t plus the total v minus v1 of the 2. So that is a v1 is clear greater than or equal to. So that is complete the proof. What we are getting it is at least 2 pendant vertices are available. At least 2 pendant vertices means if the v1 is greater than or equal to 2, vertices is clearly greater than or equal to 2 degree, then automatically it comes to the pendant of the trees. So that is our own observation of the proof. Next, it is a connected graphs. Connected graph means it is an entirely connected graph. In it is each edges are connected with the vertices, but it is not cycle. Then it is called as a tree. So it is a connected graph is a tree if and only if. Every time checking all it is a difficulty. So that I'm going for the short way. It is a if and only if it is a minimally connected. Minimally connected means it is all it is not connected. Minimally it is connected. Then we can call it as a tree. So that is a T is a minimally connected graph. So it is a T is connected. Hence, by the definition of the it follows that it is a T has no cycles. T has no cycles. For it is a T has a cycle. Then it is a removal of any edge from the cycle does not connected T and a contradiction that hypothesis on T. Thus a T is a tree. That's a capital T is a tree. Now assumes that capital T is a connected graph and it is not a minimally connected. So it is there is an edge. Say that E of T such that capital T minus E is connected. Let x comma y be the edges of the T. Edges of the T. Since x comma y belongs to vertices of the T, there it is x minus y is called as a path. So that is a P in the T minus E. Now it is a P of U union of the edges is a cyclic in T. Hence a T is not a cyclic. Thus it is a T is a minimally not a minimally connected. So it is a T is a not a cyclic. T is not a cyclic means it is a cyclics. It is a contradiction. So it is no minimally connected means it is all connected. All are connected means it is a cycle. All are cycles means it's a acyclic cycle. How we can say that cyclic? So that it is a acyclic cycle. So that it is not a connected. That's what it is a contradiction is a true. So that it is a P of union of edges is a cyclic in T. Hence T is not a cyclic. Therefore, thus it is a T is minimally connected. T is not acyclic. That therefore it is a fact that it's acyclic. It is a T is that implies it is a T is minimally connected under the hypothesis that is a T is connected. So thus it is a T is a tree that is implies that a T is a minimally connected. This completes that it's a proof of the what we are expecting. So here 3 parts we will be divided. One is a T is minimally connected, then T is a connected. It is defined that as a T is no cycles. Hence it is a removal of that one edge. It is clearly disconnected. So that it is contradicts that it is a clearly T has a tree. Next is a tree. I will take connected graph and it is a T is minimally connected. Now it is not a minimally connected. What happens? That is clearly contradiction. So that T is acyclic. So that it is a T is a minimally connected. Therefore T is connected. Therefore T is a tree. Therefore it is a minimally connected. So minimally connected will come to the tree and tree is come to the minimally connected. That is hence it is proof is over. Next it is coming to the next is G is corrected means one edge is corrected. Next G is acyclic means it is a cycle is not there. How many wedges we have? V minus 1 edges we have in a graph. Next, distance and center symmetry. Distance and center symmetry. Distance means it is any two vertices in between. The edge length. Edge length is called as a distance of the vertices. Distance of the vertices d of u comma v. D of u comma v is called as a maximum. In that maximum d of u comma v, it is a v is a any vertex of the G, so that it is e of u. So eccentricity of the vertex u of the connected graph G denoted by the e of u equal to maximum of the d of u comma v of the v is a any vertex of the u. So next is the dimensions of diameter of the connected graph G is denoted diameter of the G equal to maximum of the E of U is a U is a any vertex of the G. Now it is coming to the G is a graph and the U comma V belongs to V of G. It is distance between the U and V in the G denoted by the distance of the graph of the vertices in between the U comma V is a, if there is a, any no U to V is a path in G, then it is a minimum of the L of P is a, any U to V is a path in G. Therefore, it is a L of P is being the length of the P, the number of edges in P. So it is a distance of the U comma V is a number of edges in the P. This is the oral idea. The eccentricity of the vertex is clearly if I take it is a vertex of the U is connected graph of the G denoted by E of U is equal to maximum of the distance of the U comma V. So eccentricity of the vertex means it is a distance of the E of U. E of U is equal to eccentricity of the vertex. It is clearly maximum of the distance of the U comma V. It is all vertices highest maximum. What is it that is called as the eccentricity? Diameter means each edge of the U, which is the maximum length of the edge, that is called as the diameter of the G. Next, it is come to the radius of the connection, radius of the connected graph. Radius of the connected graph means minimal edge. Minimal edge is called as a rad G. We call it as the rad G. Next, center of the connected graph means edges of the U is equal to the radical of the G, and it is a minimum. Edge of the U is the minimum of the vertex of the G. It is called as a center. Next, it is a convention. Convention means if the G is a disconnected graph G, if we take E of U equal to diameter of the G, it is equal to rad G. It is equal to plus M here. U being U being that is any vertex of the G. Next, observe that it is if a G is a connected non-trivial graph, then dimension of the G is equal to maximum of the D of U comma V. U comma V belongs to V of G. Next, consider the following the connected graph. It comes to the U2 VU. It is if we observe that it is clearly how many edges, how many dimensions, how many eccentricities we have. Just we can check it here. I'm checking that is a E of U, eccentricity of the vertex 1, U1. Where is the U1? U1 is clearly maximum of the dimension. Diameter of the U1, U1 to U2. It means that is how many we have only. 2 are there, so that it is clearly diameter of the U1, U2 and U1, U2, then U1, U3. So that is the first one is a 1, maximum of the U1 to U1, 1, U1 to U2, U1 to U3, U1 to U4. So here, I equal to 2. E U1 to U2. How many have we have one connection? Like here, how much distances we have? 1, 1, 2, 2, 2, 3. So that it is connected graph. It is how many we have? 6. So that it is edges of the even is a 6. So that is clearly when it will be move into the outside. So that all will be the combinations we can get by the using this one. So that it is clearly having that is a 6 only. Next is E of U2. U2 if I take U2 means it's a similarly we can find out that is a maximums, all maximums, so that it is edges of 6. Next, similarly, it is going further, is all the values. It is a dimension of the G's also. Dimension of the G means it is the maximum only, so that it is 6 only. Next, rad G. Rad G means it is how many vertices we have? 3 only, so that it is a diameter of the G equal to 2 dimensions of the radical of the G, so that it is clearly satisfied. Therefore, it is a centers is clearly what happens. It is the center is clearly U8. U8 is a center. U8 is a center. Now, center of the G in the U8. Next, it is coming to the concept of following the graph. Here, U1 to U3 and U2 to U3 and U3 to U4, U4 to U5 and U5 to U4 to U6. E of U1 equal to maximum of the dimension of the U1, U2 and the dimension of the U2, U3, dimension of the U1, U4 and the dimension of the U1, U5 and dimension of the U1, U6. So that maximum is clearly 1, 1, 2, next 3, 3. How much length? 1, U3 I want to join. 1, 2, 3, 3 connections here. Therefore, it is called as a 3. 2 connections where I want to go for the U2 to U3. I want to middle one graph, one edges. How many edges we have? That is comes to the U2. So, like here, we will do the on connections. How many we have? The maximum is a 3. Here, maximum of the which one is a 3? 3 only. So, it is coming to the dimensions. E of U2. E of U2, if I take E of U2, how many we have? Like that. Above observations, we can intersect. Now, coming to the, this is important. The center of the tree is either the single vertex set or 2 elements set with the adjacent vertices. Let T is a tree with the single vertex V. Now V is the center of the T, so that it is a result of the following. Now let T be the tree with the at least 2 vertices, and capital T has exactly 2 vertices. Say U comma V, then dimensions of the distance of the U comma V equal to 1. Bracket of U comma V is the center of the T. Clearly U and V are the adjacent. Next, suppose a T has a V vertices and V greater than or equal to 3, V greater than or equal to 3. And so that it is a up to 2, it satisfies clearly. Now I am checking that is from the 3. So that it is clearly, it is not the result. The following T has a pendant vertices, and let T1 be the subgraph of the T, subgraph of the T obtained by the removing the pendant of the vertices of the T. And it is a single, I am removing. Why? Because of it is a U is a less than or equal to less than 3, all will be I remove. That is pendant of the vertices. Now it is a, what are the single observations of the tree? We have, that is I am taking that is a subtrees. It's a T1. Subtrees are the T1, and it's pendant vertices means one vertices and one edges I am removing. So that pendant vertices. It's a T1 is also the tree. One edge is if I remove, that is also tree only. Now further is a vertex of the V of the T. Edges of the T, that particular tree. Tree means it's a subconnected graph. Subconnected graph. In that edges, if I check that, it is clearly eccentricities. If I check, it is a how many. It is, for example, it is a. I'm taking the one vertex. It is connections with the various places. So how many edges we have? In that maximum, if I check, that is eccentricity. That eccentricity is clearly edges of the that what you are called as a subtree. That subtree of the V. That is comes to the dimensions of the V of V comma U. For the some dependent vertices of the U of the T. So that is any V belongs to V of T1 and E of T1 of V equal to E of T of V equal to 1. Therefore, it is clearly only one edge is connected. Therefore, vertex of the minimum eccentricity in the T is a minimum eccentricity of the T. Therefore, it is a T1, T2 have the same center. Hence, the above tree will be the subtrees of the number of the vertices. It is less than 3. Now, it is observed that the 2 vertices in between connections. So that the following are adjacent connections, and both are the elements of the centers of the tree. Hence, it is a capital T. The resultant tree has a single vertex. Then that vertices constitute the center of the tree. This completes the proof of the theorem. This completes the proof of the theorem. This is a clearly, it is a distributed vertices. It is this is the clearly we call as a T. See here, one vertex. So this is also one subgraph T1. This is also another subgraph T2. This is a subgraph T1. One edge is removed. This is a separate graph. Here, this edge is removed. This is separate graph. This is a no way connection to these two. But all are in the graph only. All are in the graph only. That particular observations of the family of the trees, how it will be connected. Distinguished to vertices, how it will be connected. That is comes to the root. Root trees are called as a binary tree. Binary tree means one is a quantity, it's connections. It is a one connection is a bifurcations will be there. It's called as a binary tree. Binary tree. If and only if there exists exactly one vertex of the degree 2, and each of the remaining the vertices is either of the degree 1 or degree 3. Let us suppose the person has a 2 male children. So the first male children has no children, and he is the second one has a 2 children. So though it is comes to the binary tree. Next is any binary tree has an odd number of the vertices. Odd number of the vertices. So here, first I will take here. Now here I will take. Here I will take. How many vertices? 3 vertices. How many connections? 2 connections. So one is a one parent, it is having the 2 children. So it is how many vertices are there? 3 vertices, 2 edges. 2 edges are there, so that it's binary. Binary tree has the 3 vertices we have. That is hence it is proved. Next, general we can write like this. Next is comes to the here V is a binary tree. Vertex it is a binary tree has a vertices. It is a V plus 1 by 2. It is called as a pendant vertices. Pendant vertices is clearly V is a odd. Now it is a proof of that. It is a T is a binary tree and V is a vertices. A V1 with a number of pendant vertices and of the T. Hence it is a T has a V1 vertices of the degree 1 and 1 vertices of the degree 2 and V minus V1 minus 1 vertices of the degree 3. Hence by the Euler's theorem on the degree of the sequence. So it is summation of the degree of the V is equal to epsilon. So 2 times of the vertices minus 1. So it is a summation D of V equal to 1 vertices of the V1 plus 2, 1 plus 3 vertices 1. So 3V minus 2. So that is a 2V minus 2 equal to 3V minus 2V1 minus 1. So 2V1 equal to V plus 1. V1 equal to V1 plus 1. Right. This is a hence it is proven. It's a simple way we have to remember. This is important for the 5 marks question. 5 marks, you will have some small questions now. So next, coming to the spanning trees. Spanning trees, it is before that I want to going for the spanning trees means it is a connections. So how many connections? All connections will by edges are connected. That is called as connection. Subgraph G. It is a tree called as a spanning tree. Subgraph I will take. In that subgraph, it is clearly being like a subgraph. Entire graph, it is being like a subgraph. That subgraph also follow that is a tree condition. Tree conditions means what is a tree? It is not a cycle. It is not a cycle. So that it is called as a spanning tree. Subgraph, it is not a subgraph. Acyclic is called as a spanning tree. So here this is called as a spanning tree. Here we can check that it is called as another spanning tree. Here also it is another spanning tree. This is another spanning tree. It is a main graph is this one. These all are the bottom one will all come to the spanning phase. This is overall observation. It is a disconnections. Disconnections means it is a one loop or it is a another. It is a wedge. This is a separate tree. This is a edges and all are the sub. So that how many components? One graph is a disconnections we can do that is a many. So that it is all are comes to the main components. Next, it is a spanning tree, forest of the G. It is a how many of the discords we can take that comes to the forest, spanning of the forest of the G. These all are the one graph he will give. Spanning trees he will ask. So that number of the all the sub trees we can get that we can go. We have. Next, it is coming to the here. 5 marks question. It is important. Every connected graph has a spanning tree. Every connected graph will be there. All of the edges are connected, so it's connected graph. And acyclic, it is not in a where it is not coming to the starting point. So it is not a acyclic. So it is acyclic. So that it is a G is a tree and it has a spanning tree of the G. So suppose the G has a cycle. G has a cycle. G1, G2 are the pairwise disjoint sets. Separate will be there. At the time, all edges I'm connecting. That is a union of edges. I am removing from the G. That is also another tree. That is also another tree. So that is acyclic tree. V of T is equal to the V of G. Because of all the G, already some edges removed. What we have is that is the pending one is called as a subtree. That is called as a T is called as a. What if we have a balanced one? That balanced tree is called as a. Also the spanning tree. We call it as a spanning tree. This is overall idea. Every connected graph has a spanning tree. Connected graph means it is already some of the edges are removed. What happens? The remaining I'm checking. After that, this is also one I will call as one of the tree. That a tree, how many are there? It is a vertices of the tree. How many so already removed after removing the edges, removing that is what are the connected graphs, what is that is both will be the same. So that is a V of T is equal to the V of G. V of T is equal to the V of G. This is called as acyclic connected. So every connected graph has a spanning. Next, if G is a connected graph, the V of G equal to V is vertices and E of G equal to edges, then E is greater than or equal to V minus 1. So under the given hypothesis, since G is connected by the known result, theorem is 11.7.66, follows that the G has a spanning tree. G has a spanning tree, and so that the T. So by the known result, we have that the edges of the T equal to V of T minus 1, which vertices of the G minus 1 equal to V minus 1. T is a subgraph of the G. So edges is clearly V minus 1. It is also a nice question. Next, now here long question, it will start from here onwards. 11.8. And see here we have one long question. This long question is Prim's laws, algorithms of the shortest path. In that he will give that is your Kruskal algorithm will be there. Steps you should be remember. He will ask that is explain about the Kruskal algorithm, and he will give the one example. And the shortest path we should be identified. See here shortest path, whichever is the minimum. So this is a oral idea. Next to Kruskal algorithm, another example. Prim's algorithm. Prim's algorithm, it is all vertices of the vertex, vertices we have, and the edges connections we have, we will take. So vertex to vertex, which is the minimum, I will connect. That is comes to this graph. So v minus 1 edges are connected. So here I will take this is a total. Vertices is a v1, v2 is a 5 smallest. So next is smallest is connected. All smallest is connected, then I will get as a graph. This is a oral idea. Oral idea. Prim's and Kruskal algorithm. You must be remember. Once you read, easily understand because of basic concepts clearly explained. So step by step procedure you should be learn and do it with the pen. Draw the graph and keep that as algorithm and do that step by step. Automatically you will get the answer. So this is comes to the Prim's algorithm and Kruskal algorithm. The Kruskal algorithm always list all the edges, monotonically increasing order lo pettali. After that, first one is the least weight I will take. That least weight is the first I will connect it. That is come to the edges point of view. That edges point of view, if all the edges is connected, you will get that is a minimum path. That is comes to the Kruskal algorithm. Next, after that, it is a Prim's algorithm. It comes to the all vertices to vertices connections. We will check it here. Vertices to vertices connections, if we connect it automatically nearest by adjacent vertices, nearest to adjacent vertices. For example, what vertices will be there? 2 connections will be there, which is a minimum. That connection I will take. So all edges are connected. Graph will be there. Graph all edges. This edge I will connect. This edge I will connect. This edge I will connect. This edge connect. All will be come to the span. That is a Kruskal. It is a Prim's will come to the all vertices. So that vertex to another vertex when it will go in between 2 vertices, which is the least. That is will be connected. Next, immediately connection will come. Edges, Kruskal, it is not like that. All edges will be connected. Here, all vertices will be connected. So that is a neighbor vertices will be connected. That is the Prim's algorithm. Some that it is we can get that is the smallest or shortest path. That is called as a Prim's algorithm. These two are the most important from the 15 marks. Kruskal and Prim's from this, it is a 115 marks question and one 3 marks or 4 marks questions you will give from the theorems. Yeah, another long question, 15 marks question also means 12 marks question means it is again we going to go for that. All the theorems in that he will take that as A bit and B bit. This is a oral idea. Okay, this is oral. It is a summary and many questions you can study the explanations and yes, if your answers also. Okay, this is a piece will be over. Next class we will discuss another topic. Okay. Any more doubts? Okay. Next class.
No, sir.
Okay. Lakshmi, Ramya.
Yes, sir.
Okay, Nana. Any more doubts?
No doubt, sir.
Okay, Nana. Right. We meet in the next class tomorrow.
Thank you, sir. Thank you.
We'll wind up the session.